Okay, so this section, if it seems like it's true because it looks like it's probably true, you're probably right. So you can trust yourself, your instincts, your intuition. Because if it looks like it's true, very likely it is, and you can run with it. So it's just hard. It's probably not stuff you've ever looked at before, but when I show you, I try to get your attention focused on it. You go, oh yeah, that makes good sense. It's just not that bad. So let me review for just a second about section 10.2 and show you and remind you that if you have a circle that is that you've got an angle opened up like this, maybe, I don't know, something like that. We tell you that this angle is 70 degrees. We agreed last section that this would be a 70-degree arc. Yep. If we have an A here and a B here, then we would say that arc AB, this is how we write it, is equal to 70. And if I put a C over here somewhere and I wanted to arc ACB, that would mean to go here through C and around to B, and we would subtract 70 from 360. And that would be a minor arc and a major arc. Yeah, remember that? Okay, now I want to do something a little different with, I'm going to just add to this. If I were to connect B and A with a segment rather than an arc, I now have, if you'll remember from section 10.1, I now have a chord, AB. Yeah? Yep. Okay. And if I were to take this, I'm going to erase to 70 so I can draw it. If I were to take this right here from here and draw a radius to that chord in such a way that the radius is perpendicular to that chord, I'm going to draw it clear out here to the edge. So that it's perpendicular to the chord, you can be guaranteed that this chord will be bisected if the radius going to it is perpendicular to it. That seems to feel right? I mean, it's not something you have to really study. Here's the other thing that the book doesn't mention, but it's very important. This angle has also been split in half. And this arc, which you extend it clear to the edge of the circle, this arc right here, put a D here. This arc BD is now equal to arc DA also. It all falls together. If this were 70 to begin with, then this is now a 35-degree arc. This is a 35-degree arc. I'm sorry, central angle. This is now a 35-degree arc. And so is this one. It got cut in half too. The arc did, by extending that radius on past the chord. The only drawings they have in there is the radius is coming right to the chord. But if you extend it further out to the edge of the circle, you end up cutting the arcs in half too. That seems reasonable, doesn't it? Yeah. They don't mention that theorem, but you'll need it to do some algebra. And one of the very first examples is that idea. So I call this whole idea arcs, chords, and central angles. Okay. It's also true that if I don't cut that in half with the radius, I just want to show you one more thing. If I've got an angle coming out like this, that's say 40 degrees, and I've got another angle over here that doesn't necessarily extend it from it or anything, and that's also 40 degrees, then you can be sure that this arc equals this one. Now that's a really crappy drawing. Let me draw that 40 a little bit better. So if that's 40 and that's 40, then those arcs are equal. But it's also true that if you connect the chords like this, and you have two 40-degree angles, then the chords are going to be equal also as segments. That makes good sense, doesn't it? Yeah. That feel right? Okay, so here's the deal. If I tell you that these are each 40, or if I just tell you they are the same, you get two things out of that. You get equal chords, and you get equal arcs that are inside those angles. By the same token, if I were to take these away and tell you that these two arcs are equal, then you can be certain that these chords are equal, and so are the central angles. So what I'm trying to get at here is there's three things. There's chords, arcs, and central angles. And if you get that any pair of them are equal, the other two pairs are automatically equal. So if you got equal arcs, you got equal chords and angles. If you got equal angles, you got equal arcs and chords. If you got equal chords, you got equal arcs and angles. You see it? Yep. All tied together. And it all makes good sense. It all seems like that ought to be the way it is. And it is. And then you got this other thing where if you take a radius perpendicular to a chord, that it bisects it. So if you're going to be asked to explain your reasoning on this one that I'm coming back to right here, it would be that radiuses perpendicular to chords bisect the chord. A radius perpendicular to a chord bisects the chord. And the book won't tell you this, but I'm going to say, and the arc bisects that arc that central angle was built onto. So if you need to explain your reasoning, you can either say radius is perpendicular to chords, bisect chords, or radius is perpendicular to chords, bisect the arc. Or you can write the whole thing. But this is what you're going to write for an explanation if you conclude something. They say, why? Well, explain your reasoning. Why do you believe that? This would be why. I will even accept this. This is in my old, before we got these books, in my old geometry classes, we just tied all three, well, this right here, sorry, let me come over here. This idea here that if you've got these equal, you got this and this equal, and any two that are given to be equal, the other two are equal, is just going to be called arcs, chords, and central angles. That's your explanation. That's fine for me. If you decide, if you know that two pairs, if you know these two angles are equal, and you say, well, AB is equal to CD, this would be your reason if you had to explain it. Okay, now there is a converse to this as well, to this one right here, and it's pretty easy. This one says, if the radius is perpendicular to the chord, then bisect it. What do you suppose the converse says? If you have a radius intersecting a chord in such a way that it bisects it, then it's perpendicular to it. So this said, if perpendicular, then equal pieces. This one says, if you get equal pieces by extending something from the center, you get equal pieces of the chord, then you can be sure that they're perpendicular. Do you understand that?
Yep.
That should make sense too. Okay, now let's just see if we can do some examples and we'll be done. If you understand most of what's happened so far, this shouldn't be too bad. Take a look at example 1. It says, in this diagram, in example 1, you got to look at it. I'm on page 546 for those of you listening if you've got a book. Example 1 at the bottom of the page says, in the diagram, circle P is similar to circle Q, not similar to, equal to circle Q. We can tell that because the radius for P and the radius for Q both have a double slash on it. That means they're congruent. So we could have told that without them telling us. It also says that FG equals JK. Those are chords. FG is in the first one, JK is in the second one, and they are equal. They tell us that. And it says that the measure of arc JK, which is in the far one, is equal to 80. How big is FG? 80. A lot of information. Little tiny conclusion. Obvious conclusion. Next one is still fairly obvious based on what I've told you. Take a look at example 2, top of page 547. And notice that we have a perpendicular at N. And it's formed by a radius and a chord, HK. Because of that, we know that HN equals NK. That's the converse one. If you have perpendicular, that's the forward one. If you have a perpendicular where a radius meets a chord, then you can be sure that chord got cut in half. And you could also be sure that the arc got cut in half. The arc, HK, also got cut in half when we extend it clear to the edge of the circle. So how long is, be very careful what I'm asking here, make sure you understand what I'm asking. How long is HK?
14.
14, not 7. Yeah, that's what I mean. Watch what I'm saying. HK is 14 because HN is also 7. So HK is 14. Now, how big is arc HK? Well, we don't know yet, but we do know that arc HJ and arc JK are equal because that radius came out, smacked it in half. And it hit that chord, cut it in half. Okay, so we put 11x equals 70 plus x. 11x equals 70 plus x, we subtract. X is 7, but that's not what they asked. They want to know how the measure, the degree measure of arc HK. I'm really struggling with it. And so we plug it in to maybe the 11x. That would make half of it 77. You see that, where the 11x is? That's half of arc HK. And so we would double 77. What's that? 154. So HK, arc HK is 154 degrees. So that was a little harder to come by, but did you understand what we did?
Yeah.
We knew the arcs were equal, so instead of being able to find x, we plugged it back into one of the arcs and doubled it because plugging it into one of them only is half of what we need. Everybody clear?
Yep.
Okay, moving on. The next one is, it's a kind of a construction. It's actually kind of a cool thing to know, and it can be useful. I've had to use it in a shop over here. I made my mom. This is a story. I know. Just stay with me. It does have a geometric conclusion. But when I first started working here, well, let's go way back. When I was in the 9th grade, I was in a shop class and I made my mom 2 end tables. They had octagon-shaped tops and they had these really pretty lathe legs. I learned how to lathe. I loved it. It's like doing clay, except it's much more permanent. Lathing is wonderful. I love it. Very artistic. I'm not very artistic, but I am there. And I wanted to build my mom a coffee table that where the legs coming off of it match the legs on those end tables. So the whole thing would fit together. And in looking it over, 4 legs coming off it made it look really stupid, and it made it look like more like an elephant. And so my uncle suggested, why don't you make 2 big columns coming down, and then some of those pretty little legs coming off that come off like this, some legs to hold it, and then an arch in the middle just to connect the 2. Well, I had to make these I had to glue together a whole bunch of mahogany, 1-inch planks of mahogany, and make a block that was like that, was square like that. I don't know what these people say. It was about that big. I put it on the lathe, made it circular, made it beautiful, did it just right. But I was supposed to attach the legs, to the tabletop with a big bolt through the center, big lag bolt. And then attach that piece to the bottom of the table. You understand? Maybe you don't understand. But anyway, my problem is that as soon as I got it off the lathe and I was happy with it, I had to cut them the same length. So what I ended up doing is, by the way, when you lathe something, when you go to the center of it, if you start out with your block like this, you put this thing in there and it makes these 4 little things like this, and they bite into it really hard, and then there's a big thing that goes right in the center of that, and these 4 things help keep it so it'll spin it. And it's I wish I could show you the thing that goes into there, though. It goes in like that, and you pound it in with a hammer before you put it on the lathe, and then it holds it so that it'll spin towards you and you can cut it without it slipping. You understand what I'm saying?
Yeah.
Well, what happened was, after I got finished lathing it, I cut that off I couldn't find the center anymore because all I had was this big circle like this, and I had to find the center. That's not usually what we have to do. Almost always when we study circles, they give us the center and then we do something with it. But here's something really cool. To find that center, I didn't have much to do because I'm a geometry student, but the shop teacher had no idea how to find that center once I had cut it off, the shop teacher that we had. So I looked it up and made sure I was doing it right, and here's how you do that. It's really cool. All you got to do is take a pencil and draw with a straight edge, draw 2 chords, and it doesn't matter which 2 chords. I'll do that one and that one. You just straight edge, get yourself 2 of those. Then you got to take a compass or measure very, 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 very carefully and find the center of this. I mean, the middle of that, so that this equals this. And you got to fill that so that this equals this. And then you grab your square or something that you know for sure makes a right angle. And you make a right angle here and you extend it out like this. And you make a right angle here. And you extend it out like that. And where they meet is the center. I think it's pretty cool. Find the center of a circle. You need 2 chords that are perpendicularly bisected. You extend those perpendiculars until they cross and you got it. You may never have to use that. And if you do, you probably won't remember it. So call me if I'm still alive. And I will remind you how to do it. It is just not that hard. And that's what they're trying to explain to you in example 2. If you'll notice that's almost exactly what they've got there. They've got these 2 chords. We cut them in half, make them perpendicular. And where they cross is going to be the center of this deal. And this is how they did it. This is a sprinkler that they're trying to figure out. It says 3 bushes are arranged in the garden as shown. Where should you place a sprinkler so that it is the same distance from each bush? Same thing. They've got the chords there. They haven't got the entire circle, but where those 2 perpendicular bisectors cross is going to be, they're going to be on that circle. We'll hit all the bushes with the same amount of water. Yep, kind of a cool thing. All right, so third page. Take a look at example 4. If we get this one done and you understand it, then we should have no trouble with this assignment. Example 4 on page 548. Take a look at the diagram there to the left of example 4. Here's what it says. In the diagram, QR equals ST equals 16. So find it. QR. Now we're talking about when they don't have an arc or a segment across it, they mean the length of a segment. So QR, y'all find QR? Mm-hmm. Y'all find ST? Yep. Each of those is 16 units long. Now we know, based on the markings right there, that QU must be 8 and UR must be 8. Y'all agree with that?
Yep.
Okay. CU equals 2x. Find CU. CU equals 2x, okay? And CV equals 5x minus 9. So that's the red and the blue algebra statement there. The question says, what's the radius of circle C? What? How are we going to find that? The length of it? That's almost nothing, it looks like. Now, since they told us that ST and QR, those are both chords and they're both 16, means that both CV and CU must be equal. Because they're going to equal chords. Does that make any sense at all?
Yeah.
Okay. Actually, that's based on the theorem just above, which I didn't make a big deal out of. But if the theorem up above says that, if the chords are equal, then the distances to them are equal. And by distance, we always mean perpendicular distance, shortest possible distance. If two chords are equal in a circle, then the distance to those chords from the center has to be the same. That's what that theorem said that I just skipped over. That's my fault. I should have skipped it. It's another theorem. Okay? So that means that we could set 5x minus 9 equals 2x. We probably would have done that anyway because that's what we normally do. Besides that, it looks like they're the same way. It feels like they ought to be if they're going to equal chords. Okay, so we write 5x minus 9 equals 2x. Find x, that's going to be 5x, no, 2x, 3x. Sorry, 3x equals 9. Moving the 2x over here and subtracting and the 9 over here, x is 3. Which means that those lengths are what? 6? 6. So those little pieces of the radius are 6. I'm going to write down what both of them are. They are CU and CV equal 6. Would you all buy that? Do you understand this statement right here? You see how we got it?
Yeah.
Because once I found the x, I had to put it in here or in here, and either way, you're going to get 6. But that's not the radius length. Only a piece of it. They want to know the entire radius of circle C. How are we going to find it? The answer is, you can see it right here. I know my book's upside down, but it's right. If you look carefully, compare this diagram that they gave you to work with and the diagram we're going to find the answer to. What's different?
They have a green line.
They added a green radius. The green radius was drawn so perfectly and in such a great way that it completed a triangle, of which we know both wavelengths. So if you want to find the radius of a circle, and they really don't have any individual radiuses that are just hanging out by themselves without crossing chords and arcs and everything, draw your own. Draw a radius that completes a triangle. That green one completes a triangle where UC is 6 and UQ is 8 because it's half of that 16 they gave us. Then you can use Pythagorean theorem. The trick is to draw your radius so that it completes a triangle. Then you can use Pythagorean theorem on it. You could draw a million different radiuses here. But if you draw a correct one that completes a right triangle, then we could have also connected, by the way, we could also drawn a radius from C to S. You see that? I could have drawn the radius from C to S, and that would have completed the triangle there on the bottom, which is also, well, it's a right triangle with CD. Ooh, that wouldn't have been good. No, you don't want to do that one. No, because you can't tell for sure what SU is or SV. Anyway, completing it with the one on top where we have that bisected chord, we get 2 of the 3, and we would take 6 squared plus 8 squared, which is 100, and square root, which is 10. And so the radius of this circle would be CQ, the trick to draw your own that completes a triangle. Okay? Everybody good or not?
Yeah.
Cool. Here's your assignment. You're going to love this. There's only 8 to do. I know. These assignments are short because it doesn't take much practice to master what's going on, mainly because your mind always tells you this is true anyway. Just practice with it a little bit. Only 8 problems, 3 through 17 of them. Okay? So that one's not going to be bad at all. There you go.
That's it.